Welcome to lecture 15 on risk management and insurance. Until now, we assumed that the utility function is upward sloping and that the consumer is risk averse, so the utility function is concave. So upward sloping and concave. In this lecture, I would like to be a bit more specific and really look at some special utility functions. So we will use the functional form. We will look at special functional forms of the utility function. The first one is a CARA utility function, constant absolute risk aversion, and the functional form, okay, we have here. So utility, okay, depends on wealth, and we have here actually the Euler figure and negative power. Now, this functional form, this function qualifies as a utility function because it's upward sloping. If you do the first derivative, okay, then it's positive. And if you do the second derivative, then it's negative. So we have an upward sloping function, it's concave, and here actually we know really the specific form of this upward sloping concave function. Now you know how to take the derivative. Again, okay, naturally the constant does not matter. Constants don't change, so it does not matter when you do the derivative, when you calculate the rate of change. And then you take you just write down the E again with the power, but then you have to multiply with the derivative of the power. So the derivative of the power with regard to wealth is minus alpha. That's because you have to do this because of the chain rule. So minus then actually becomes a plus here. So we have here a positive rate of change. The function is upward sloping. Now, if you do the second derivative, simply again write this down. It's very easy to take derivatives of the Euler number. So that's really why we use actually continuous compounding nowadays in finance. So you have it here again, and so multiply again with the derivative of the power, the chain rule, and you have here now a minus sign. Okay, the second derivative is negative. Okay, so this utility function is concave. You have risk aversion. Now it turns out that the parameter alpha is the coefficient of absolute risk aversion that we have discussed in the last lecture. The coefficient of absolute risk aversion is defined as the second derivative divided by the first derivative. Look this up again in the last lecture. So we now just simply plug in for the second derivative and for the first derivative. This comes from the preceding slide. We have here the second derivative. So plug this in. This is the first derivative. And so everything cancels out, and so you have in the end alpha. So the coefficient, so the parameter alpha up here is actually just the coefficient of absolute risk aversion. So that's why we call it here the constant absolute risk aversion utility function. Now, with CARA utility, this coefficient of absolute risk aversion is independent of wealth. Okay, it's just a constant. And this implies that the willingness to pay for insurance, measured in dollars, for a given absolute risk does not depend on wealth. Remember, the willingness to pay for insurance depends actually here on the consumer's risk premium role, which we discussed the past two lectures. So we take that formula and plug in for RA, and so we just plug in the alpha here. Maybe we go back and have shortly a look at the formula again when we did it the first time. You see here, we said the risk premium of the consumer is actually approximately equal to this expression here with the coefficient of absolute risk aversion. This was equation 31. We derived this, we did this approximation using those Taylor series. So here I'm now using equation 31 and I'm plugging in for RA. So I'm having alpha here, and you see here now the risk premium of the consumer, which really determines the willingness of the consumer to pay for insurance. This risk premium does not depend on wealth. And that's actually counterintuitive. Just think, okay, maybe you have a car. You're lucky you have a car. Maybe the value of the car is $10,000. And then actually you may buy insurance. Against so the car, when the car is stolen, okay, then you'll get your money back. So you will buy insurance against losing the car, okay, so if it gets stolen. Now let's assume Bill Gates has a buggy, a golf buggy, okay, that's also $10,000, and also naturally also Bill Gates has a risk that his golf buggy will get stolen. But probably Bill Gates does not worry about it. You see, he has $50 billion of wealth, so he will not worry if his golf buggy is stolen, okay, and he loses the $10,000. It hurts you to lose $10,000, a car with a value of $10,000, but Bill Gates, who already has $50 billion wealth, okay, he will not worry about it, okay, if he loses $10,000. So Bill Gates will not buy insurance. Bill Gates will not insure his golf buggy, but you will insure your car because it represents a substantial part of your wealth. Now, this model here predicts that also Bill Gates buys insurance. You see, it does not depend on wealth, okay, the risk premium, the consumer's risk premium. So it's independent of wealth. So the tendency to buy insurance measured in dollars is the same for you and for Bill Gates, who has actually 50 billion. So for a given risk of losing $10,000, okay, Bill Gates also will buy insurance according to this model, and that's naturally wrong. That's counterintuitive. So something seems to be wrong with this model. Still, I must say, this utility function is used quite often in research, particularly in agricultural economics, because it's so easy to deal with mathematically. And naturally, we then just applied to standard situations where people have some kind of normal wealth, and we do not apply it to Bill Gates. So you can actually, for example, in agriculture economics, maybe you can apply this to a farmer. Okay, all farmers are have similar wealth. Okay, here in Australia, maybe $1 or $2 million. Okay, the farms are quite valuable, and that's it. And so we can use this utility function. But there is no farmer around like Bill Gates, okay, with $50 billion. Okay, so it gives here the wrong prediction. We still use it, okay, in research, but in extreme cases, this would actually not work. So let's try a different model, constant relative risk aversion. Now here you have the functional form again. And that's just simply, okay, a power function. So gamma is again a parameter, okay, and here we have wealth. Now you can write down this a little bit different. Okay, let's do it even if it's not so easily done. Okay. So, we have wealth to the power. And we divide by 1 minus gamma. And then actually subtract 1 divided by 1 minus gamma. So I break it up here. Okay, so that's the same thing. And this, you see, it's just simply a power function. So that's a function like y equals x squared. So that's really, okay, so we have up here the square. And so maybe you divide by a constant a. And you subtract the constant b. So basically, I have here a power function where actually we also divide by the power, and then actually we subtract here a specific constant. So we have a power, but then actually we just also divide by that constant power, and here we have another constant. It's a power function. Again, this is actually a utility function. It is increasing strictly concave for positive wealth. So the first derivative is actually positive. Just do the first derivative here. So the power comes down, it cancels out. And then naturally this constant part does not matter in the rate of change. It doesn't change, it's a constant. So that's becoming 0 when you do the first derivative, when you calculate the rate of change. So that's positive. So we have an upward sloping function. The second derivative is negative. You see the power comes down and you subtract 1 up here, minus 1. So I introduced here this additional bracket. So what I have up here is actually just minus gamma minus 1. Minus gamma minus 1. And so that's now negative. So I have a concave function here. So again, this is a utility function of a risk-averse person. Now it turns out here that the parameter gamma is the so-called coefficient of relative risk aversion. When you go back to the last lecture, the coefficient of relative risk aversion is actually just the one of absolute risk aversion times wealth. Remember, the coefficient of absolute risk aversion is the second derivative divided by the first derivative. Now, if you multiply with wealth, you get the coefficient of relative risk aversion. Just check it out again in the last lecture. Now, here we can again plug in those derivatives from the preceding slides. So let's take this second and this first derivative and substitute it in here. Again, everything cancels out and we get gamma. You see this w to the minus gamma cancels out against the w to the minus gamma up here. And then I have here a w to the minus 1, which cancels out to the w here. Okay, so I just have here the minus gamma, and then the minus minus becomes a plus. So I'm getting here gamma. Now, if you have CRRA preferences, then actually the willingness to pay for insurance measured now as a proportion of wealth is independent of wealth. Now here measured as a proportion, not in dollar terms, but measured in percent out of wealth. And that's actually, okay, not a bad assumption. You see, before we had actually the willingness to pay for insurance, and it's measured in dollars. Okay, does not depend on wealth. And this really led to the problem, okay, with Bill Gates. So actually he worries about dollar terms. He worries about losing his golf buggy of $10,000. And like you, he buys the same amount of insurance, or almost the same amount of insurance. So that seems to be a bad model. Now here, it's measured in percent of wealth, measured as a proportion of wealth. Naturally, Bill Gates also worries about losing maybe 10 or 20% of his wealth, and then will buy insurance. So I take now the version of earlier of this approximation here of the risk premium, okay, where we express the risk premium as proportion of wealth. That's a rho star. We did this also in the last lecture. You see the rho star is actually all rho divided by wealth here in equation 33. And this depends then on the coefficient of relative risk aversion. Okay, so I take this where it's actually the risk premium is expressed as a percentage of wealth. I work with relative risk aversion, and so I just can plug in now here's a gamma. So actually, the percentage Bill Gates may actually worry about losing 10% of your wealth. You buy insurance. Okay, you have this risk premium here that determines your willingness to pay for insurance. And then Bill Gates also will worry about losing 10% of his wealth. Okay, maybe in this case $5 billion, and maybe he also will try to get insurance. Okay, that's probably then will not be so easy for him to buy insurance for such a large amount. But okay, he will also would like to buy insurance, so he will behave like you. This assumption, okay, seems to be quite realistic, or more realistic than the early one with absolute risk aversion. Now, if you convert it back to dollars, so let's write now again as a risk premium here with dollars. So I use the absolute risk aversion. The absolute risk aversion is a relative divided by W. That's what you have in equation 34. You can look that up. So I plug in the gamma. So if you think in dollar terms, okay, how much insurance people want to buy, okay, this actually now declines with wealth. So in dollar terms, Bill Gates will buy less insurance. He does not worry about his buggy of $10,000. But in relative terms, losing 10% of wealth, Bill Gates also will worry about it. Okay, so here actually wealth does not matter. Okay, that's not so easy to see. Okay, so give this a bit of thought. So the predictions of the constant relative risk aversion model seem to be more realistic than the ones of the CARA model. Now let's go now to higher order derivatives. When in the preceding lectures we did those Taylor series expansions, remember on the left side of the equation we had a first order Taylor series expansion. On the right side we had a second order expansion. You see we had a problem here. Okay, that this equation 25, we cannot solve it for rho because of Jensen's inequality. You are not allowed to write the expectation into the nonlinear function. And that's why we did here the Taylor series expansion. On the left side, we did first order. On the right side, we did second order. Now, let's look at the right side. Let's now use on the right side third order expansion. Okay, this would reduce the mistake. Now, so on the right side, I'm now here on the right side of the equations, I have now here this additional term for a third order expansion. And actually, I write now here two faculty. I did not write the faculty when we did the second order expansion, those two terms, because naturally two faculty is actually just two. Okay, but with three, so actually the faculty really matters, 1 times 2 times 3. Okay, but here it's just 1 times 2. So whether you write the faculty here or not, okay, doesn't matter. Okay, so we now plug this in, we use this, we work again through those equations that we had last time, and we get this new term here. Now, sigma to the third power, that measures you the skewness of the distribution of x. So the consumer has a risk premium will have this additional term. This we had before, but this we have now on top of it. Now let's assume, okay, the loss function, the loss is skewed to the left. By this I mean okay, distribution is skewed to the left. If you have here a very thin tail, and then maybe something like that. Okay, so let's assume, okay, high losses may occur, but okay, with a low probability. We have this thin tail to the left. So we have actually this extra risk of high losses, even if actually, say, occur with a low probability. Now, a prudent consumer actually will take this into consideration and will be willing to pay more for insurance. So we speak about the prudent consumer, and that happens, okay, he will be willing to pay more for insurance, okay, if actually this third derivative here is positive of the utility function. You see, if one is positive and that one is negative, sorry, those two are positive. The first derivative anyway is positive, and let's also assume the third derivative is positive. Then by assumption, now sigma to the 3 power, the skewness is negative. Okay, we have negative skewness, we have a thin tail to the left. So I have negative and negative, so I'm getting here actually a positive term. So the risk premium will increase. So a prudent consumer will take account this distribution of the losses that we have here. Losses with a low probability. We have actually very big losses. Okay, so we are here have those negative figures here, and so actually the sigma 3 is negative. That's actually a third moment. Okay, it measures the skewness, and if on top of it, so we have here a negative figure here, negative gives me positive, and if anyways the utility function is upward sloping, so that's positive, and this here, okay, if that's also positive, then actually I have overall here a positive term which adds to the risk premium that the consumer is willingness to pay. Now you can go on, and you could actually add a fourth order term on the right side of the equation. Okay, when you do the Taylor series expansion. The fourth derivative, actually this fourth moment measures you the so-called kurtosis. it measures you, okay, whether you have extra mass in the tail. So whether actually your probability distribution has fat tails. Maybe we draw one. Yeah, okay, where pointer options. Yeah. So you have now here probability distribution. Maybe you have a normal distribution here. Now with bigger kurtosis, your tails are fatter. You see, you have now fatter tails. Okay, it's not the best graph, okay, that I have drawn here. So you have extra mass in the tail. Now again, this extra risk, you see you have here an extra risk compared relative to the normal distribution. You have the fatter tails, so you may have bigger losses, you also may have bigger profits, but you have better risks, you have a higher risk. And so again, the consumer actually probably will pay more for insurance, is willing to pay more for insurance. And that actually happens when the forced derivative here is negative. So a negative forced derivative will give you this result. So let's here again go back. So I have here negative. The first derivative anyway is always positive. We have an upward sloping utility function. Now let's have the kurtosis. You have this extra kurtosis. We have the fatter tails. So that's positive, the force moment. Remember down here. So I have here now a minus sign. I have here a minus sign. And I have up one here, the force derivative. So I'm getting here now again a positive term. And so this will actually drive up. Okay. It will drive up here the risk premium. So willingness to pay for insurance will increase. And they say, okay, that's actually temperance. They use the term temperance in it, but it's not entirely clear, okay, why they use this term for it. So that's actually quite fascinating. You see here actually how economists work. Nowadays, in modern economic models, we use utility functions. We try to model a behavior of people. Now here in the insurance market, we try to actually explain and model the behavior of people going back to the utility functions, going back to their preferences. The utility function measures their preferences. And actually the behavior of people here does depend on the second and on the third and the fourth derivative of that utility function. You see, okay, with this extra kurtosis and with this skewness to the left, okay, the person will be willing to pay more for insurance. So the second, the third, and the fourth derivative of the utility functions matters here. But that's actually quite extreme. Okay, that's a naturally, and we would like to know those utility functions. And that's what they try to figure out in econometric work. And that's naturally not so easy. But that's typical for modern economic models. You go back to the preferences of people, you model those preferences with utility functions. And now here in this extreme case in insurance, even the third and the fourth derivative and of those utility functions matters. Okay, in other examples, okay, when you just look at the behavior of people in the market, okay, how many apples they buy, how many bananas, okay, then you don't go to the third and the fourth derivatives. Okay, but it's very similar. Also, you look at the utility function, you look at the preferences, and then you actually determine the demand of the people for commodities in the market. So that's what you do in microeconomic classes. Now, we would like to know those utility functions. Now, the findings of CRRA and Pratt that absolute risk aversion falls with wells is generally accepted. That's the CRRA utility function. We have shown this. I have it here in equation 45. You hear wealth is down here. So when wealth actually increases, rho will fall. Now here it's in dollar terms, it's a rho, it's not a rho star. So that's actually generally accepted. So the concentrative risk aversion utility function may be superior to the constant absolute risk aversion function, but also the CARA function is actually still used. Particularly, I've seen it being used very often in cultural economics because it's really maybe it's a bit easier to deal with it mathematically than the CRRA utility function. Arrow, he's a very famous economist. He got a Nobel Prize in economics, not just for this work here. Okay, he did a lot of things in economics. Now, when you so the question is, if we have the constant relative utility function, what is now actually gamma? What is the size of the parameter gamma? Now, macroeconomists typically say, okay, gamma is equal 1 or 2. Now, financial economists work with a little bit higher gamma, 2 up to 4. They actually do estimate gamma using microeconomic data. That's actually data of individual investors. That's microeconomic data. Macroeconomists, they use data for the entire economy, not just for individual investors. And they actually arrive at the somewhat smaller gamma. Okay, let's just discuss something that you can actually discuss in the tutorial. Gamma equals 1. Now, this should ring a bell with you. Gamma equals 1. So you see I have here the constant relative utility function. Now, if gamma equals 1, yeah, okay, you divide here by 0. So that looks like trouble. But actually, it works. Gamma may approach 1, and you will see in the tutorial what then will happen if gamma equals 1. We will get a very simple utility function. Actually, we will get the logarithmic utility function. So as gamma approaches 1, okay, it still defines the utility function. It will become the logarithmic utility function, and you can actually prove this with so-called L'Hospital's rule, okay, L'Hopital rule in calculus. So it's actually a nice application for L'Hopital's rule. So don't worry about gamma equals 1. It gives you the logarithmic utility function. Now, expected utility naturally cannot explain all types of observed behaviors in risky situations. You see, some people actually behave completely different. We probably believe, most economists probably believe that it gives an approximation, it holds on average, but some people actually in risky situations may behave completely crazy. Okay, so then actually expected utility theory will not explain that. Other people, there are a lot of psychological theories here. Okay, maybe those arguments and actually a good explanation. And the expected utility theory, okay, cannot explain actually those psychological factors, which also play a role, okay, in risky situations. So maybe actually then some economists actually regard the expected utility theory only as a normative theory. You see, it's a theory how a rational agent should behave, how a rational agent should behave when that agent maximizes utility, is concerned about his utility. But maybe psychological arguments are also important. And that's actually, okay, is discussed in so-called behavioral economics or in behavioral finance. So the expected utility theory, you may actually just use it as a normative theory, how a rational agent should behave. But other people really use it as a so-called positive theory that really explains, okay, the behavior of people in the market. So makes this distinction between a normative theory and a positive theory. Now, there are two paradoxes, the Ellsberg paradox and the Allais paradox. Now here, in those two situations that the paradox look at, actually people can behave in ways that conflict with expected utility theory. Now Allais, he's a French economist. Actually, he's also in physics. So actually, he's the only person. He has actually he got the Nobel Prize both in physics and in economics. So that's quite remarkable. Ellsberg is also actually somebody who is well known, particularly in my generation. Ellsberg actually published the so-called Pentagon Papers. Now, the Pentagon Papers were during the Vietnam War, like WikiLeaks, he stole actually a lot of documents at the Pentagon and published those documents about the Vietnam War and made a book out of it, and this became very influential. Now, Ellsberg and actually also, he was there was court proceedings because he stole those government documents, but in the end, actually, he did not have to go to jail. Now with WikiLeaks, with WikiLeaks, okay, he's in bigger trouble. And you can actually, it would be actually interesting to think about why did Ellsberg get away and why Aswang of WikiLeaks now today does not get away with it. Something things actually, maybe something has changed in the political process. This was the so-called Pentagon Papers. He took a lot of documents from the Pentagon in the United States, from the military, and published those documents. But okay, he also did actually here, okay, it's a so-called Ellsberg paradox. He contributed actually to expected utility theory. Now, behavioral economics or behavioral finance explores deviations from expected utility theory. So you could actually read here this chapter here in Eckhout, and then somewhat easier, okay, you have it here. Okay, so behavioral economics nowadays is very, very popular. You have also psychological arguments that behave as that are supposedly to explain okay, the behavior of people in financial markets. But really, expected utility is really just, it really remains a primary model of behavior under risk. Now, students really first should learn about expected utility theory, and maybe then later on they go into behavioral economics. Now, it's very bad if people only know behavioral economics and they don't know about expected utility theory. There's a lot of people like that in the financial markets. But if you really want to have a secure grounding, okay, in financial theory, you have to start with expected utility theory, and then maybe you add, okay, behavioral arguments. It's also done here actually in insurance. Okay, the appendix we already did. So that actually finishes now this chapter. Thank you.